All right, so we're getting into the meat here of exponential functions. And remember, we're talking about functions of the type y equals some amount of something, in this case population, times whatever the multiplier is, which is a percentage that's either added to or subtracted from 100% as a growth rate. And then x is either years, months, hours, decades, whatever it might be. And that's all we were basically doing, is we're just converting the context here into math. So let's look at the first problem here. It says that the blue point has a population of 39,000 people. The town has been seeing its population decline by 10% every year. So the population's not growing, it's actually going down. They lose 10% per year. If this trend continues, what will the population be in 10 years? So we got a lot of good information here. We've got a decay rate of 10% or decline. We know that the time involved is 10 years, and we know that let's just do that there, make that a little smaller, that the population that starts, so that's basically A, and this is the value of x. The question is, this relates to B, and some students think that, oh, 10%, that means B is 10%. That's not actually quite the case. What we have to do is we have to remember that it's really, the original amount, and then B is found by either adding or subtracting whatever percent of growth or decline is taking place. So in this case, if it's going down 10%, that means we're going to take away 10%. So we've got 39,000 people, and 100% that start the beginning of each year minus the 10% that are lost each year, raised to in this case, 10, because we've got 10 years. So this is, remember, I'm using percent notation here, but what we have to remember to do is really to express this number right here as a decimal, right? Because if I continue to just write it as a percent, I'll be overstating it by 100 times. So what we'll do is we'll just type this function right here, the way I've got it written, into the calculator, which I'm doing right now, 39,000 times, I'm just going to use parentheses here, 0.9 raised to the 10th, and that means that to the nearest whole number, the population that we see is we get 13,598.459. Obviously, it's not possible to have 0.459 people, so we're being asked to round to the nearest whole number, and of course, all we look at is this. That number is not 5 or above, so we're just going to leave it. So in Ixl, I would literally just type in 13,598, which is what I did when I was getting the screen capture, and of course it was correct, so let's keep on going. 64 grams of radioactive europium. How much will be left after 30 years? If it's half-life, you have 64 grams of radioactive europium. How much will be left after 30 years if its half-life is 15 years? All right, well, what the heck do they mean when they say half-life here? That's what we're trying to figure out. So we've got, here's the relevant information. We've got the 64 grams. Oh, that's a little dark, isn't it? Let me make that a little lighter. Here, let's try that. A little pinkness. All right, so 30 years. Half-life, 15 years. That's the information. So again, as always, I'm looking at y equals a times b to the x. Well, a is 64. X is 30 years. Oh, sorry, let me take that back. X is the question we're trying to figure out. In this case, we have to be careful. The half-life is 15 years. That means, this is a scientific term you've probably heard before, half-life is the amount of time it takes for a radioactive substance to have decayed to the point where only half of its mass is still there. So what you've got to think about here is x is not actually years. X is how many periods, how many 15-year periods have taken place. Because if I do it that way, my multiplier, b, is just 0.5, because half, it goes down by half every 15 years. I want x, the unit x, to just represent how many of those periods of time have gone by. So in this case, with the information we've got y equals 64 times 0.5. Again, 0.5 because we're losing half of it, which is 50%. And the question then is, how many 15-year periods are there in 30 years? And the answer to that is 2. So I will now go to this calculator, and I'll literally type in 64 times parentheses 0.5 to the second power. And that means that after 30 years, there will only be 16 grams left, because it's going down by half. So it goes from 64 grams, 15 years later it's cut down to 32 grams, and then another 15-year period goes by, so it's been a total of 30 years, it's cut in half one more time, and so that makes sense that 16 grams would be our answer. 16 grams. Okay, similar situation, we've got a, oops, let me just erase that, didn't mean to make that one noise. A colony of 195 bacteria doubles, colony of bacteria, 195 doubles in size every 125 hours. What will the population be 250 hours from now? So we've got a situation here where I've got 195 to start. They're doubling, which means it's 100% more every 125 hours. So X is going to be how many of those have happened. Not how many years or hours or minutes, but how many time periods, each of which was 125 hours. So in this case, since they're asking about 250 hours, well, that's just 2 of these. So that means in our problem, X will be 2. So we've got y equals a b to the x. In this case, y is 195. Now, if it's doubling, that means it's 100% plus 100%, which is 200%. But again, remember, this number is always expressed in decimal notation, not as a percentage. So I just had to relocate to the basement so you guys don't get the sound of barking dogs distracting you. Okay, so when we were just working on this, I said this is what we're going to do. We're going to take 195 times 2 to the second power. And so when I compute the value of 195 times 2 to the second, I get that that now has actually reached a population of 780 bacteria, because it's doubled twice, right? We went from 195 as an initial, and if I double 195, that means after the first 125 hours there were 390, and then that doubled again after the additional 125 hours. And so that's why that answer makes some sense. 780. Enter. Again, we've got half-life, okay, so we're talking about a multiplier of 0.5. The half-life of a radioactive kind of bismuth is 5 days. How much will be left after 10 days? Well, that means since the half-life, the period it takes for that half-life to occur is 5 days, that means in our case, X is how many 5-day periods have taken place, which is 2. So again, we've got the y equals a times b to the x. We start with 576, and the half-life, again, means that half of it will be there, so 50% is gone. So 100% minus 50% is 50, which expressed as a decimal is just 0.5. And so what I'm going to do is calculate this value, 576 times 0.5 squared, or to the second power, and that means that now it's 144. And again, you could double check that. It's pretty easy to do the math and realize that if I take 576 and only half of it is there after the first 5 days, it's dwindled down to only 288, and then I divide that again in half, and you can almost do the math mentally, really, it's not hard. You see that it's 144 grams left. All right, this looks like a really pretty complicated problem because it's all wordy, but if you look at it closely, it's not much. Colin and his friends are doing a physics lab on air pressure. First, they fill a balloon with air until it reaches a pressure of 480 kilopascals. Kilopascals, potato. I'm not quite sure if I'm saying that correct, but I think I'm close. So they've got this balloon that they filled up. So this is our starting value. This is where we're beginning. And then what they do is they They prick a little hole in it, and the air then begins escaping, and they measure the pressure of the balloon over time. And according to their measurements, the balloon appears to be losing pressure in the balloon at a rate of 10% every hour. So it must be an incredibly small hole. They must have used a tiny little needle. Obviously, because it's going to still, most of it's there after the first hour. So if this trend continues, what will the pressure be in 17 hours? So you might be wondering, will there be any air left in there? And of course, we're just making some assumptions here that this really behaves this way. So here we have a situation, y equals a times b to the x. Let's talk about our values here. The initial value is that 480 kilopascals. Pascals? Pascals? I don't know. I don't feel like it sounds right no matter how I say it. B, if they're losing 10% every hour, that means that the amount that's still there can be found by just subtracting that 100% that you start with minus the 10%, which means it's 90%. But again, remember, we're always going to use decimals to represent, because the decimal's the actual number. 90% means 0.9. It doesn't mean 90. So, and then x. So that means, in this case, it's pretty simple. The time period is hours. And so x is just 17 hours. So we'll just plug numbers in here and say we've got 480 times 0.9 to the 17. 480 times 0.9. Sorry, I hit the wrong button there. To the 17th power. That means that to the nearest tenth, 17 hours later, the pressure has gone down significantly. And to the nearest tenth, I get on my calculator 80.05. So to the nearest tenth, 5 and above, we're going to round that up to 80.1. Now keep in mind, we have to think about the practicality here. Exponential functions predict that things will never go all the way to 0, when in fact we know that there will come a time when this thing actually reaches 0. So, but it's still reasonable within the range of time that this problem is setting out for us. A robotic company sells robot vacuum cleaners, maybe Roomba or one of those. Since the newest model was introduced, let me use the pointer. Since the newest model was introduced a while back, the old model has seen its sales fall by a consistent 10% per month. Right? Because you know how technology is. Like nobody has a Palm Pilot anymore. I don't think, except for as a collector's item. If 2,000 old vacuum cleaners were sold this month, how many will be sold 5 months from now? So these are declining in popularity. And what's probably misleading about this is in real life, this percent might not always be the same. This percent itself might be growing, at which point the relationship is a little more complicated. But for simplicity's sake, let's just use our tried and true exponential decay model. So we know that this month is the current period. We don't know anything about the past, so 2,000 represents the value that we're starting with, A. And if they're losing 10% a month, let me just clarify that. A is 2,000. Take away 10% a month, just like we did on the last problem. That means my multiplier is 0.9. And x, since this rate is based on per month, that's just 5. So y is 2,000 vacuum cleaners last month. Only 90% every month for the next 5 months will be sold. So we've got 2,000 times 0.9 to the fifth. So after 5 months, there will be only 1180.98. So to the nearest whole number, that means that in 5 months, instead of selling 2,000 a month, they're only going to sell 1,181 vacuums. Still a lot of vacuums, but it's definitely decreasing. Last one. All right, half-life. We know that means that our B is 0.5 and that it takes 79 days. So X is how many of those take place. And our initial amount is there. So you can see how these problems start to become fairly routine after a while. We start with 2368 grams. Our multiplier, because it's a half-life, is B. And then our X is how many 79-day periods took place. Well, how do I figure that out? it's real easy. Just take 316, divide by 79. And it turns out that 316 divided by 79 is 4, so x is 4. So we start with 2,368 grams. It's decreasing by 50% each 79-day period, and we want to know after 4 of those, or 316 days, how much is left. 2368 times 0.5 raised to the 4th. That means that there's only 148 grams left after that period of time. So these are a little complicated, but they start to make sense once you get the hang of it. I'm sure you guys will have no trouble at all.